Okay, so we're ready to get started. Good morning. My name is Karin Strauss. I'm an innovation strategist here at Microsoft Research Redmond. And today it's my pleasure to introduce Torsten Hoefler, who is going to talk about ML for a high-performance climate and Earth Virtualization Engines. Torsten is a faculty at ETH Zurich and has been working with high-performance computing and performance-centric system design for a really long time. He's been involved in many cool projects, including the specification of creating the specification for MPI, computer architecture, programming languages, systems is all within reach for Torsten here. And lately, also a lot of work in machine learning and optimizing such algorithms. And as you can see, also on applications of machine learning. So across the stack work coming from Torsten. Super exciting to have you here today, Torsten. Thank you so much.
Thank you very much, Karin, for hosting this. This is an absolutely wonderful opportunity to talk a little bit more about something that I don't usually do, as you've just heard. So I'm more of a lower level architecture person, but I like cross-stack.
Microphone? Microphone?
Oh. Okay, so thank you very much, Karin, for the wonderful introduction and hosting me here. As you just heard, this topic is not necessarily in the means of my core research, but I really like reaching out, and this is actually a larger effort that I'm going to talk about, a worldwide effort by a very large number of people. Because we are all who have been living here in the Seattle area for the last couple of years have realized that temperatures are rising and have realized that heat waves are coming. Just 2 weeks ago, actually 3 weeks ago at this point, we had a pretty bad heat wave here, and if you've been here, that was quite annoying because many of my friends, and I'm somewhat an old-time Microsoft consultant at this point, so since 7 years I've been here every summer. And it has been getting hotter over time, and now we seem to be crossing a threshold where the ACs are not good enough anymore. I mean, the ones that are installed, because traditionally in this area you wouldn't need that much air conditioning or any air conditioning like 10 years ago. So we don't want this area to look like this, which is a desert that comes out of the co-pilot image generation mode. And actually, if you look a little bit more, and just this July, these are press releases from a couple of weeks ago here. Hazy skies, Seattle, bad air, really poor air quality. And if you've been here in 2018 and 19, then you know what really bad air means. So I've unfortunately been here. And this is not because the Seattle area is super polluted in the sense of industry or something. It is actually wildfires, and it's mostly wildfires in the Pacific Northwest and Canada that are burning down millions of hectares of land and are actually causing very bad pollution here. But what's even worse is that they cause a whole lot of trouble, as you can see here. Over the years, the tree cover loss in Canada last year was a record year. So multiple millions of hectares were just burning down for no reason. And you see it even in the global tree cover loss. There was a significant outlier that was just the Canadian wildfires in 2023. So this is getting problematic slowly. And it's getting problematic mainly because we are observing that the Earth is getting warmer and warmer and warmer and warmer. And this is just an animation of the historic data that we have. So it's not a projection into the future. This is an actual observation-based metric. And you can see up here in our area, it's turning really red. so somehow that may be a problem. So what do we do about this now? Well, what we do about this now, we define actually all kinds of policies. And the question is, what do we define in these policies? I'm not a politician. I don't want to talk about policy at all. But what I want to talk about is actually understanding the change a little bit better. And here I want to start with a quote from Jensen Huang, because you may actually think that, and everybody knows Jensen, I suppose, probably the most successful entrepreneur in the modern history, running a $3 trillion company based on AI. Or it was recently $3 trillion. But what he says, he has a deep interest in climate simulations and climate prediction. And what he says on record is climate simulation is basically impossible today. Predicting the average temperature is possible. That is very important. So we understand that the average temperature is increasing. But an image like this on top, we wouldn't be able to generate into the future with high capabilities, because because the world doesn't care about average. You care about your own region. I am living in the Pacific Northwest. I care about my region. And the unfortunate piece with averages is that if something gets really cold, it may make up for something getting really warm, and still both places may be uninhabitable at the end. So that's one of those problems. So what do we do? Or what did we do? Well, we know that we ran these climate simulations into the future. We understand that on average we are warming the Earth, but we really want to understand what does that have as an impact locally. So somehow we need global simulations for local impact. And last year we got together to discuss with a very large number of people. And most of these people, in fact, are not computer scientists. In fact, I think I was one of 3 or 4, maybe even 2 or 3, depending on how you count, computer people in that group of people. And these scientists were mostly meteorologists and climate scientists that met, and we together tried to understand what do we have to do on the simulation side in order to get a good local prediction at a global scale. So we really want to understand questions like, I'm an olive farmer. If I plant an olive tree today on my land in Africa, when the olive tree bears fruit in about 10 years, will it still be possible for the olive tree to live there? So, I mean, these kinds of planning situations is very important. So I don't want to talk about policy, what we should do. I want to talk about what do we do to understand the change we have to deal with, because at this point it's unavoidable. So we have to, it's changing, we have to face it. It's very hard to stop things. So this is what was the purpose of this meeting. We got together and discussed in that meeting. And what we figured out is, first, we understood what computation means in the context of climate simulation. So let me run this through, basically Jensen's impossible argument, because he really says impossible today. What does this mean? Why does he say it's impossible? Well, first of all, we have to look at the resolution of a climate simulation. So it's a global simulation. We have about 511 million square kilometers on our planet. It's quite a large planet. And now, if you simulate anything, you would discretize the planet into some form of grid, and you would represent a certain area on the planet by a grid point. So now, and this grid point has a resolution. So if you say 1 million meters here, then every 100 million times 100 million meters, there's one number representing a variable at this grid point. So it's very coarse-grained here. And if we have a 100-meter resolution, or let's say 1 kilometer resolution, we already have 511 million grid points to represent the planet, right? So just to read this scale. Okay, so first we realize, as we go towards the right, towards finer resolution, more and more physical processes are resolved by the physical simulation. So if my resolution goes up, so if I'm resolving more pixels, basically, my underlying physics that's driving is basically the Navier-Stokes equation, are simulating more and more processes directly. Today, because the Earth, the whole atmosphere is a dynamical system, and it's a chaotic dynamical system. So you probably all know about the butterfly effect. So if I do this, I may be creating a swirl here that goes off to become a tornado somewhere else. It's very unlikely, but it's possible. So we cannot simulate every human doing this, right? That makes no sense. So what we always have is we have so-called subgrid processes. So we have the simulation until a certain resolution in the grid, and then we have what's called a parameterization in physics, in the climate simulations, that is somehow a heuristic where somebody observed what's happening when the grid is in that state. So it's kind of machine learning for poor people. So, or machine learning before machine learning was invented. A good friend of mine, Björn Stevens, who talks about this a lot, he calls it hokey-pokey physics. Okay, so what do we now do? At 100-kilometer resolution, it's basically continental scale. Like every grid point is kind of a country, or parts of big parts of a country. At 25-kilometer resolution, we actually begin to resolve very large cyclones. So they begin to form naturally in the simulation. We don't have to parameterize them. At about 1 kilometer, we resolve pretty heavy storms. So now it gets interesting. So if you just go down to that resolution, the simulation will have emerging effects that automatically behave like a storm. So that's physically realistic. So that's getting interesting. Only if you want to resolve these little clouds, that many of those we have here in the sky in this area, that needs about 100-meter resolution. But they may or may not be super important. The unfortunate thing is clouds are one of the most important things for climate simulation. Right? Because they block the sun, they rain down on you, so it is actually one of the most important high components. Now, if you just look at the storage required for this, on the left side, I can easily run this on my laptop with my USB stick. On the right side, I have 50 petabytes for a single variable simulation for 30 years. 50 petabytes is quite a lot, but it's just a single variable. We actually need exabytes for a single simulation campaign to run this at 100-meter resolution. This is bad. But now, what you also do, because if you run one simulation into the future, you do a weather prediction. But we all know that the weather prediction is not very accurate more than 10 days into the future. So it drifts off somewhere else. So what we typically do in order to predict the climate, we don't want to predict what is the weather at this day, at this moment, in 1 year from now. We want to predict what is the probability distribution of possible weathers 1 year from now on this day. Right? So is it going to be hotter on average or not? But how do we do average as well? What we do is we actually run multiple simulations, so-called ensemble simulations, into the future, such that we have many weather patterns developing, then we do statistics over the weather patterns, and then we call this the climate. Right? So that's basically it. So we have to not only look at a single simulation, but we have to look at many simulations. So that's another cost. Each of those simulations takes a 50 petabyte of storage to store. So climate scientists disagree generally in how many of these simulations are needed. So some people say, well, 10 is okay. Some people go into the thousands. Of course, the problem with this is you can have a lot of ensembles if you have a coarse resolution, or you will have less ensembles by definition if you have more with the same compute budget with higher resolution. So as we increase the compute power, we can run more ensembles or higher resolution. There was a large disagreement in that meeting. Which one is better? So it's not so clear. But the nice thing is what we can do is we can now draw lines in this plot. We can now say we have a supercomputer, this is the Levante machine in Germany, a climate supercomputer, that for a single simulation in 1 simulated year per day, so for a 30-year campaign, you would be occupying that computer 100% for 1 month, right? We can simulate at 5 kilometers, and after 30 days, we would have a 30-year campaign at 5 kilometers. Right? This one ensemble member. Okay, so now we can draw other supercomputers, more powerful ones. The fastest one in Europe is LUMI. We would go to 2.5 kilometers. We would go worldwide. Frontier or Fugaku, the fastest supercomputers on the planet that we publicly know of today, they would go to 1.5 kilometers. And then we had a huge discussion in that meeting. What would we actually want? Like, what would we need in order to predict local climate at a reasonable accuracy? So these are the domain scientists that tell us. And domain scientists, well, first of all, there we cannot compute today because we don't have a machine that fast. And the domain scientists put the goal there. It's like, great. So it's impossible. This is what Jensen means by it's impossible today to do these simulations, because that's what these people want. They want some ensembles. So it's still somewhere in the couple, like tens or so. But at approximately 1 kilometer resolution, because then these emerging effects of clouds actually really show up. And you can increase the accuracy of the simulation quite a bit. So this we wrote up in this article, basically requirements, what we would have to do for simulating the Earth at again, global simulation at local scale. Like extremely computationally demanding. So what can we now do in order to get there? Help these people. So that's my job. I'm the person who builds supercomputers. So we can build faster supercomputers like we've been doing over the last 40 years, basically. Well, over the last 40 years, we've been largely watching Moore's law make our machines faster. That's unfortunately not going to work these days. So Moore's law kind of stopped. So we can build larger computers that use more CO2, produce more CO2 in the process. So that may be a not so preferable process, but we could. Or we use machine learning to just change all of that. Right? I want to talk about both in the remainder of the talk. How we build faster supercomputers, how we use them more efficiently, and how we use machine learning in the process. Okay, but back to these people. We actually looked at a very specific simulation run that may be useful to run this with a real model like the icosahedral non-hydrostatic weather and climate model. They're great with names. It's called ICON. So it's about 630,000 lines of Fortran code. Right? So everybody loves Fortran. So if you run this 30-year simulation, you would need, for one trajectory, right? For one ensemble member, you would need 11 zeta ops, which would be 13 days full power on an exascale supercomputer, so something like Frontier, and you would generate 344 petabyte of storage if you write these at relatively high frequency. So that's a 3.2 gigabyte per second sustained output that this simulation is running. So it's quite massive. It's really, really a massive problem. And this is just one trajectory. Right? You need 10 or so. So, yeah.
But the 1% efficiency is that in compute efficiency?
Correct. That is so that machine, this exascale machine, has a certain floating point peak performance, and these codes today they run at about 1% efficiency of that peak performance. But we have to be careful here because these machines are tuned for matrix multiplications, machine learning problems. These codes are very far. The simulation codes are very far from machine learning workloads. So which really means this efficiency should not be over-interpreted in some sense, but it's really sad somehow, right? Because they're all memory bound.
Yeah, that's what it was.
They are memory bound.
Memory bound.
Yes, you would need a different architecture to support these kinds of codes if you wanted to increase the efficiency. My personal view on this is we don't necessarily need a different architecture. This is just the wrong metric. We just have to accept that the floating point units, which are relatively cheap on chip, they're just not utilized well. But we should be reporting memory bandwidth utilization, for example. But this is extremely tricky. I have another talk on this. It takes 2 hours to explain. So, because memory bandwidth is not so easy with peak because there's caching involved, reuse and all that stuff. Very complicated, I/O complexity. So we go into very, very shaky territory. So let's stick to climate. So what we need for these climate simulations to really work and also to involve AI techniques that we have developed over the past years, we need to work on data. So we can look at observation data and simulation data and train models from those. We need to look at compute. So we can do high performance computing like we've been doing the last 40 years. But we can use AI to accelerate those, right? And we should look at models. So we can now invent new techniques, basically, because most of these simulations are driven by the Navier-Stokes equations or by the Eulerian equations. So models that very intelligent humans derived a long time ago. And these models are very small complexity, but are applied to a lot of data. Like the Navier-Stokes equation, I can write down on the whiteboard. An AI model has so many parameters I cannot write down. So what AI models typically do, they have more complex models that we cannot write down easily. We don't even understand how they work, in fact, trained on data. And we apply them to this problem. So we can do this here as well in climate. And then typically, the climate scientists work in this tool chain. So they have a lot of observation data, lots of satellites, planes, stations, balloons that go up every now and then. Then they run these simulations, either weather and climate, or climate. Then they post-process the simulation data, and then eventually they go to climate insights. So that is the tool chain I want to describe, or the workflow that is used today. So let me start with the observation data. So observation data is interesting. So observation data is spread all through our planet. Actually, over the last couple of years, we had an exponential growth in observational data sources. There have been these step changes whenever satellites were launched. These satellites, there are 2 different types of satellites, polar orbiting and stationary satellites. So polar orbiting satellites, they fly around the Earth and take extremely high resolution pictures of the Earth. They generate petabytes of data per day. Right? Most of this is compressed, discarded because it's too much, but they have a really high resolution cameras, and lots of those. We have lots of satellites covering the Earth. The only problem is, this is not on a dense grid. This is wherever my sensor is, wherever my satellite flies over at a given moment, I get a picture. And it's about 1,000 kilometers wide, but here I'm not sure. I think it's hundreds to thousands of kilometers wide. But it's very unevenly distributed. And also, sensors on Earth are very unevenly distributed. There are not so many sensors in the Atlantic or in the Pacific, but there are lots of sensors in Europe or the United States. Actually, in the United States, most of the sensors are on the east and the west coast. So I'll show a picture in a couple of minutes. But what we need is we now need to turn this mess of sensors into a regular grid on the Earth. Because for an atmospheric simulation, the grid point over the Pacific is about as important as the grid point over New York City, where we have many more sensors. So we now need to deal with that very sparse sensor data and it's called assimilation, assimilate this into a dense grid. That's problem number 1. And what we contributed in my group is basically we thought, hey, let's use an AI technique. Of course, there are many techniques how to do this. Like people do this since many, many years. But we thought, hey, there are these diffusion models that make these fancy pictures. By the way, both of these pictures come out of diffusion models run in Copilot. Why wouldn't we use a similar technique, which is called in-painting, for filling the field? Because we have these sparse measurements, but now we just want to fill the remainder of the field with the statistically most likely filling given the points we have. Right? And if you're a machine learning person, you're immediately like, sure, that's a diffusion problem. So if you're not a machine learning person, let me just give you a 5-minute overview of how diffusion models work. So what they do is actually they start from a real image, like you can see here. They add random noise, and in multiple steps, 40, 60 steps, but they learn the reverse function. They learn, after they've added the noise, a denoiser. So for each step, they train a function that undoes the step. So the loss function is very easy to define, right? So you want to undo the random noise added. And at the end, you get a thing that you can run from random noise to a real image. like multiple steps, because you add noise, you train the backwards function, and the function trained, then it's just a denoiser. It's very funny that this works. It's extremely cool. I could go more into detail. But at the end, what you can do with this, you have a denoiser here. You can basically say, well, I want to take. Is there a question online? Okay, cool. If there are any questions online, just interrupt me. I'm happy to go into details. But if you just want to like remove this dog and replace it by a yellow cat, you would use the same thing. Like you would just use all the pixels that are there as a bias at the input, and then ask the denoiser to refill the remainder. So it looks like this if you look at it in practice. So it fills in the original pixels, but it replaces the dog, which we've just masked out, with something else. And we're going to use exactly the same idea to, instead of the original pixels here, we take the measurement values of the observations we have, and we fill in the remainder of the field. Like that's the high-level idea. I think at this point, everybody understands we don't need to go much into detail. If you really care about the detail, there's a paper at this year's ICML that describes that in excruciating detail with lots of data. I can quickly show you the model, but it's also, again, I don't want to go into the greatest detail because it's intuitively clear how it works at this point. So it's a lot of, like we plug in a GraphCast model, which is a simple forecast model, a neural network-based forecast model coming out of Google. We condition it on the state. We use the model again in the diffusion context, running these multiple iterations. Then we refine this. We, of course, have these masks because we need to know where the sensors are. Like we need to extract the masks. And then we add a little bit of noise, as is typical in these models. And that's it, and we get to the assimilated data. So it looks quite complex, but most of these infilling pipelines look exactly the same. So there's no big deal here. The key innovation that we have actually is we use a soft masking, because if we just have one pixel, these sensors are very small. Like they're like centimeters big typically, but they are going to fill in for a kilometer-wide grid point, right? So now you need to do some softening of these sensors, which is where we have the hard mask in detail. We apply some kernel with a max convolution, and we get to a soft mask, which is also very well known from picture or image generation or image blurring and things like this. So we just use a kernel that's very similar to Gaussian blurring. So at the end, we take a GraphCast forecast. So here is just the temperature at 2 meters of the Earth. We look at the observations, which we just sample randomly here from a data set. We blur those observations, so now they're wider. And then we run this thing that's called Diff-DA, and then we get to the assimilated data. And you see, well, the screen is not high enough resolution to tell you the difference, so it's already kind of good. If you now look at the difference function, if you subtract these two, now basically red is bad and blue is bad. So that's the error. We're now subtracting the golden copy from the generated copy. We see that there's actually a little bit of a problem with GraphCastNet. So we use GraphCastNet just for assimilation without our scheme. So there's especially in Northern America, there's a bit of an issue, in Northern Asia. Here, if we just interpolate, that's another baseline we can choose. If you just interpolate between those, I mean, if I have two neighboring points, I just take the interpolation. Then you see a lot of error here in South America and also Central Asia here. And if you look at our method, there's basically the general error is much better. So now there is still error, of course, but it's significantly lower than any of these two baselines that are typically used in practice. So the assimilated data is really better than all of the inputs. So that's a nice early sign. Here is actually a map of the real observation stations on Earth. You see lots in Europe, lots in Eastern US, not so much in Asia. But actually the Asian thing is because China doesn't contribute a whole lot to this database. They have more sensors, and we ask them to contribute more. This is the WMO, World Meteorological Organization database of these sensors. So the challenges are that we have these satellites that make these strips here because they fly around the Earth. We have various different sources at various atmospheric heights, pressure levels. So it's actually a real mess in practice. Like it's not as easy as I was talking about, but at the end we have a coverage of about 0.05% of the grid points that we want, and fill in from there. So this works reasonably well, but it needs some integration with the real weather service.
Is that percentage before or after the softening?
That is before the softening. That's just the grid points that are covered by some station.
And once you do that, do you know what the number is?
It doesn't get much better. It doesn't, but we don't know what the number is, but it doesn't go above 0.1% if I would have to guess. So it's still very, very, very sparse. So we have more data for meteorologists, but let's not go into detail. So we have a cool idea for the observation, how to use AI, right? dissemination models. Now I want to go a little bit more into the simulation side. So what can we now do? Because we have all of this AI hardware now. I guess we know Microsoft even announced this Maya 100 chip that I was involved designing on the system architecture. So we have specific hardware built for AI. And actually, if you look into the future, pretty much all hardware that is big business is going to be built for AI. So floating point 64 is going to go slowly away, which is a huge problem for that community, right? Because they base all of their computations on FP64. And now, basically, industry is phasing it out. So that's an issue. So we now need to understand what to do. So we have two options. We could either say we take the traditional simulations and port these simulations to the modern AI systems. Like a GPU today, I would call a modern AI system. So we port them to GPUs. And then we optimize for what AI looks like. Or the other thing we could do is we could just say, well, we just replace the simulation with AI, like what I just did in the first part. Again, in the meeting we discussed, people were very skeptical of replacing full simulations with AI for reasons that are very obvious in some sense. Because if you look at any of today's weather models, they're good for a 7-day horizon. But if you keep running them autoregressively, so you would say 7 days, then another 7 days, then another 7 days, based on the output of the previous one, none of those conserve physical properties. None, like zero of these successful weather forecasting models conserve physical properties. So we've actually done this. You would be running out of water on Earth in about 20 years. Because it just disappears as a rounding error. So that's a problem. So there are various ideas how to deal with this, but this is why people are skeptical. Like climate scientists are skeptical that you can run these models 30 years into the future. For 7 days, they're actually better than today's simulations already, so there's a huge hope, but we still need to understand how to actually put those together. So we follow both paths. And I want to quickly give you an overview how to do both of these things. So here we have these GPUs, and we have this Fortran code on the right side. So what do climate scientists today do pragmatically? Well, they take a thing that's called OpenACC, Open Accelerator Annotations, and they annotate their Fortran code. Basically, they say this is a do loop, which is for computer scientists, that's a for loop. So this is a do loop, and they add an annotation and say, well, this loop is independent, so you can parallelize it on a GPU. Which is now a huge problem if you're a computer scientist, because first of all, you realize, well, there's a lot of this red stuff. This is additional code that the climate scientist doesn't want to write or even see. Because it's just, well, it tells the compiler that this is a loop. Yeah, sure. OK, great. The other problem is if you're now a software engineer, you realize that actually you duplicate the code. Because the do here says it's a do loop. This up here says it's a do loop. But it adds an additional property that it's an independent do loop. So now if you change a single character in this do loop and do not update this, you have the most horrible bug you will never find. Right? Because now you just have race conditions. Depending on what thing you run it'll give you different results. And we've had a lot of experience debugging for months just to realize that one of those statements is wrong. And especially if you have a 630,000 lines code, that is really bad. There's even an ISO norm that says don't do this. Right? OK. Actually, if you look at real codes, they look like this. And just to give you some statistics, so there's a code that has 13% of the lines of code just this junk. In a real code, the icon code, which is not such extreme, but it has about 4% of the lines of code, the 630,000 lines, is OpenMP and OpenACC, so these annotations. So this is not great for climate scientists. What we developed in my group is a programming environment where we basically say, well, we need to decouple the domain scientist from the applied scientist that then translates this to a real architecture. So the domain scientist should not be seeing these annotations. Domain scientist writes the code. And if you know anything about machine learning, so I'm sure you all do, this would be the PyTorch or the TensorFlow level where you don't deal with any architectural details. And then this would be the implementation of PyTorch and TensorFlow in the machine learning context. And this would be the optimization of kernels in PyTorch and TensorFlow. So we pushed the same idea. We actually came up with it before PyTorch and TensorFlow. but it's a very obvious idea. So you want to really separate the concerns. The climate scientist does that. The applied mathematician does that. And the optimizer does that. And then we came up with this tool chain, which then translates all of that to optimize GPU, CPU, and FPGA code. And the idea is that on the climate scientist side, we have tens of lines of code. For example, the GPT-3 model, which drives, or the GPT model family in general, which drives all of Copilot and open models, as well as ChatGPT, this is less than 100 lines of code in PyTorch. right? So it's a very, very high abstraction level. But then at the end, the kernel implementations are tens of thousands of lines of code in that. And we are generating, in our case, so here in our case, we hope that we have hundreds, so we want to be slightly better than that toolchain. But at the end, we will get thousands of generated lines of code. So we have done this with the real code. So this is how a visualization of the graph looks like. You can zoom in further, and you can zoom in further, and you will actually see code. Again, 600,000 lines, so the performance engineer is shocked by this. There's no way that you can deal with this. So basically what we do, and I don't have enough time to talk about this here, is we have a thing that's called transfer tuning. So we embed these codes into an embedding space, and we look up in the embedding space with vector search good optimizations that we have tuned before. So it's very much like if you know k-nearest neighbor, if you know RAG, retrieval augmented generation. This is retrieval augmented generation we generate optimizations based on a database for a specific architecture for metaprogramming, for optimization of codes. Right? So that's a different talk. In case you're interested, this is also on YouTube. But I want to stick to the climate code here. So we have one code that we looked at, the Cloud SC code, which is about 2,500 lines of Fortran 95. The nice thing is, why did we choose this code? Because the ECMWF, the European Center for Medium Range Weather Forecasting, if you're in the United States, you know this as the European model. Like that very often is shown as slightly better than the American models for predicting hurricanes and things like this if you watch TV. So they have ported that code, which is very important for them. That's their central model for predicting, Cloud SC, so that's the clouds in their model. They ported it to C as well as to CUDA, like manually. And so we have a comparison, which is very nice. So the first thing we realized, we had the original Fortran code, which is what they wrote. The first thing they realized is that the C code is 40% slower than the original Fortran code, right? So actually it's pretty sad news for C, but good news for Fortran because Fortran is very fast. We ran it through our framework. What we found is that in our framework, and this is the code generation thing I showed you earlier, we get about 5% faster than the Fortran code. Okay, nobody cares about 5%, but at least we are not as slow as the C code. But then if you run it on multi-threaded, you get 20 times faster than the baseline. And then if you run it on GPU, which we can also do automatically, we get 100x speed up out of the whole exercise without changes to the original code. So we take the original Fortran code and compile it to a GPU-based system and get 100x speed up over a single thread execution on a CPU, right? So that's quite nice. And it is about as fast as the manually ported code. So the green lines here is the manually ported code that they did. They took them about 4 engineers, as far as I remember, for 6 months. So this is quite substantial effort that we were saving. For us, this took about a week for a PhD student. Cool. So now we can actually help the climate scientists with the simulation side. And now the last part I want to go into is how do we handle the simulation data? Because as I mentioned, the simulation produces hundreds of petabytes of data, actually exabytes of data. As a comparison point, the ECMWF, the European Center for Medium Range Weather Forecasting, they are producing 1 petabyte of simulation data per day. Okay, that's their output today. Peter Bauer, a good friend, has given lots of talks about this, and he said this is unsustainable because if you do this every day, that's an exabyte in 3 years. Right? And now look at what an exabyte of storage costs. It's a lot. It's 10 to the 18 bytes, right? So that's a lot. So somehow we also tried to help there. And first of all, we looked at how this data looks like. It's multiple variables in stacked 2D fields. Like it's 2D technically, but then we have the atmosphere going into the height. So we have multiple levels. That's somewhere between 10 and 70 levels, depending on how you discretize the atmosphere. So you run your simulation forward. So you start from an initial state, so you run steps. Right? So typically they're in the seconds, but every 15 minutes or so, every 30 minutes or every hour, you write the state of the atmosphere to a file such that you can later replay it. So you store some of these time steps. Right? And then when you want to look at something like how is the weather in the Pacific Northwest in 20 years, you only look at a very small subset of this data. You don't look at the whole Earth for this thing, but you look at very small, sparse points typically. So this is what we took into account. And then the key idea I want to communicate is we actually take these dense fields, we train some neural representation, some neural network, whose job it is to exactly reproduce these fields. So if you're a machine learning person, that's an autoencoder. But we see it differently. We want to specialize this network to exactly that data. So we want to do massive overfitting to have this network exactly reproduce this block of data. So here it could be 1 year of a variable, and it's typically a 4-dimensional block of data, which is quite nice because we see that we can get about a 3000x compression. So which means we throw away this original block, we just keep this network, and this network is 3000x smaller, reproduces the original block when queried, right, to some approximation, and it's 3000 times smaller. So this is quite nice. The only problem is it's very expensive to train this network. So compression is very expensive. Decompression is very, very cheap. So, but we wanted to see this as a kind of a proof of concept. I could go more into details how the network itself looks like. It's a Fourier-basis network. It's okay. I mean, again, you can look this up. It's inspired by a thing called ForecastNet that was published by NVIDIA a while ago. I will tell you some problems with that approach in a minute, but that's basically what we did. So we compared to existing techniques. So we have the reference on the left side. It's uncompressed. We have the neural network compression 1000x, a little bit more than 1000x in the middle. And then we have another compressor that's SZ3. It's an arrow-bounded compression mechanism that scientists very often use at the right. So that's about 350x. And you already see that SZ3 introduces a lot of artifacts here. I mean, it already looks kind of blurry. We see that nicely we preserve general shapes. It's not perfect. I mean, if you look at those, they're slightly different, but it's okay. But now one problem with the Fourier basis is we are Fourier transforming things. And what does this mean? When we Fourier transform things, we're doing a frequency expansion in some cyclic function space. Right? So it's either cosine or sine. And then we chop it off at some point. So we chop off some frequencies to compress it. It's very much like JPEG works, where many of these compression mechanisms work. Unfortunately, high amplitude effects get chopped off. So here in this case, in our compression, we actually kind of lost the Hurricane Matthew, which is not very good because the problem is in climate analysis, it's exactly what you care about. You care about the tails. But with that compression mechanism, you kind of lose the tails. So not great. Right? So this was our first approach to do something. This is also the biggest criticism of AI methods when it comes to prediction, because they may be losing the tails. Because the AI method, we use the standard network, network that looks very much like the network that's used for prediction. Right? So they may not predict the extreme events as well. There are lots of fixes today, and this is relatively old work. But this is one concern we always need to watch out for if we do AI-based predictions of weather and climate. So how did we fix it? Well, that's actually an interesting thing. We have wavelet compression. We invented a slightly better scheme that now doesn't use cyclic basis function, but it uses wavelet basis function that can be arbitrarily steep. Like this was also the change from JPEG to JPEG 2000. They changed the basis from a cosine basis to a wavelet basis. And wavelet basis, if you use the hard wavelet, it's basically a 0-1 function. And then you have very steep things. And then, by the way, there is a Nature paper that just appeared recently that gets a 9x compression and is about as good or slightly worse than what we were doing at a 1000x compression. So there's a lot of interest in this area. And these machine learning methods are very, very, very promising. Because now if we use the wavelet compression for this hurricane, it's perfectly maintained. It's also perfectly maintained in the bit rounding case, but they only get a 10x compression while we get a 1000x compression. So changing the basis, the message here is that if you do any machine learning method for AI for science, the basis function is the most important thing to tune. Of course, you also need a good loss function and everything, but most people miss this. The basis function is your fundamental concept to approximate in this area. So that's working well. This is great, so we get very high compression ratio. And with that, I would like to conclude basically and summarize again a little bit what I mentioned. So I talked a little bit about this, the EVE effort where people got together to understand what is needed to run climate simulations into the future. What do we really aim for in this field? I talked about how we can implement those and help those people with transfer tuning and many, many, many other techniques. I talked about innovative techniques where we completely change the tool chain. This is far out, so this is not going in production next year. Diffusion, by the way, the assimilation is run every 3 hours on massive supercomputers by every weather service on the planet. The techniques we use today are not diffusion-based, but I strongly believe that in about 5 to 10 years, this will change. These diffusion methods are extremely promising. They will replace much of the traditional toolchain. But it's going to take, because they have an operational thing, so it's always super slow. And then we looked at also using AI techniques for compression. Those are relatively ready, actually, to go into production, because the problem is ECMWF, for example, they simply discard all the data. The NASA, the satellite data, they discard a lot of that data, or they compress it with worse compression schemes that get a worse result, because they have a limited budget for data and their incoming data stream is bigger than that budget. So these schemes they find very fast adoption because they're just better. While the assimilation schemes, people have already purchased these very, very large supercomputers. Then there is one thing that I find extremely cool about the last part, the case study on compression, that actually we have 40 years, bless you, we have 40 years of history of our Earth in an archive. Like the image, the video I showed you at the very beginning, that comes out of that archive. So the ECMWF maintains an archive that's called ERA 5, reanalysis 5. They're now working on ERA 6. That is literally all the sensor data that we had for the last 40 years. It starts very sparse and goes better and better and better, so higher quality. But they store the assimilated fields. So not the sensor data, but they store the whole field, which gets better quality towards the recent past. And that is about 5 petabytes of size. Right? So it's very hard to manage that data set. And it's one of the major impediments for climate scientists to actually do analyses. Like, I'm working a lot with climate scientists that are like, oh, I need to download all of this data and run through all of this. And then they do kind of funky approximations because they can't manage all of this data. And then they do approximations where I'm like, I'm not sure if that is the right thing to do. I could give you some examples, but maybe that should be taken offline. But if we have this compression by 1,000 times, the 5 petabyte, there'll be 5 terabyte. And that's pretty much a USB hard drive that we have today. Then any climate scientist, you can go and you can run on your laptop, you can produce that video that I showed you at the very beginning, or you can produce that video at higher resolution for the Pacific Northwest area. You can look at every weather event that was observed over your home the last 40 years. It's actually quite cool. I mean, this data is really nice. Any weather event is in there, right? Because it's just a record of and you can have it on your laptop. And then generally, typical advertisements. I'm working in Zurich. We are now in a wonderful high-rise building, which is very special in Zurich. So if you're interested in academic visits or a job as PhD student or postdoc, let me know in this area. We are growing heavily because it's a very important area. So thank you very much for your attention, and I would love to have some questions if you have any.
Data set you mentioned and the trick of actually compressing it, there's the cost of decompression. So it fits in the laptop. Does the compute for decompression also fit? I remember you saying this is very cheap to decompress, but is it proportional?
So we have these two methods. We're still developing better methods as we speak. I actually had this morning a call with a PhD student who's working on this. So we're pushing this further. The first method, the neural network-based method, takes a long time to compress because you have to train that neural network. But decompression is just inference. And with inference accelerators, I mean, my laptop here has a Ryzen core in it and has AI engines in it. Like, it's the same as a language model, right? So this is very cheap. It's extremely cheap to decompress. Compression is a training thing. And then we're developing much cheaper techniques that are very similar to image compression techniques. Like if you compress your JPEG 2000, for example, they just manually define these kernels that fit well the average image you see on a picture. So now the average image you see on a photograph is very different from one of those climate fields. So we are developing methods that are working better for these climate fields, so domain-specific picture formats in some sense that enable high compression. That is not yet ready. But that's kind of the vision going towards it, such that compression also gets cheap. Because right now, we have only cheap decompression, but not so cheap compression. So you would need a supercomputer to compress the thing, which is quite annoying.
I was more curious about the decompression.
That is not a problem. That's really, really, really cheap.
Yeah, with emerging hardware specialized for that.
Exactly. But we always improve and make it even cheaper, but yeah.
Questions? Any
I
questions?
thought the characterization of climate as like all possible weathers in the future was really interesting. I'm curious, do all people attempt to model it through this like ensemble sampling of weather, or are there attempts to like explicitly model the climate distribution headed into the future?
Oh, everything is being done. And this is a huge field. So the subset I'm looking at, the subset I understand, I don't understand all of these mathematical tools where they look at variance analysis and I don't know what. Subset I understand is the weather prediction. But then there are lots of tools, statistics tools basically, to understand how many ensemble members I need. But the common way to run simulations is to run with ensembles. I would say 90% of the people do this. And then others, you could also assume that you run one simulation forward and you kind of carry the standard deviation of that simulation. Right? You carry some statistical property, but the problem is then you will have one trajectory and kind of following a statistical property with it that doesn't seem very accurate to me, but some people do this. So there's a huge variance in the field. So it's generally the way, it's also pretty funny, the way climate scientists agree on the correctness of their simulations is they do model intercomparison studies. It seems like, to me, exaggerating here, every climate scientist has their own climate model. Like so they have something in the garage and do this. And then they come up and say, oh, I've made a prediction now. The Earth is going to explode in 20 years. And then other climate scientists, I'm not sure about your prediction, but then the discussion always boils down to, well, my model is different than your model, and how do we reach agreement? There is a thing that's called CMIP, what's it called? The Collective Model Intercomparison Project, that is kind of a consortium of lots of climate scientists. It's pretty powerful. They collect the input of the model for a defined problem. So they basically say, well, look, we want to simulate the average temperature of the Earth in 30 years. Here's the starting conditions. Here's the defined problem. And then everybody can submit, it's like the top 500 list for supercomputers. Everybody can submit their simulation result and simulation code. And they have like 70 entries or so. So it's a lot. It's quite a serious effort. So I don't want to belittle it. It's a huge effort. And then they make these predictions. But now if you look at the actual distribution of the potential warmings of the Earth, the error bars are really high. So it was something, like one model even said it would cool down, but that was just one. I think they removed it as an outlier. But it was somewhere between 0.6 and 2 degrees, which is a difference between okay and we are totally on fire. So somehow the accuracy is not very high. And this is why many people, in fact, in addition to what you just mentioned, run different models in these ensembles. They don't just run one model because the models also disagree. They run different models, which is even more complexity. So this is very, very hard because each of those models makes different approximations, especially in the microphysics, which is the thing you don't resolve. And the way they came up with this is like the hokey pokey physics. So it's basically they have experiments. How would the atmosphere behave at that resolution if there's, let's say, a temperature gradient. In 15 minutes, the temperature falls by 20 degrees. The humidity was, 80%. If it falls by 20 degrees, then you shall have rain because water condensates and it rains down. This is now an exaggerated example, but this is literally how these microphysics work. They look at manually crafted heuristics, I would call this as a computer scientist, that then show some effects like rain, hail, and all of that. And you could argue that any machine, and this is why I would argue that these machine learning models, how I would explain that today's machine learning models are better. These machine learning models would learn these hokey pokey physics based on the data, because it's also a difference how a cloud forms over ocean and how a cloud forms over land. Many of these physics macroparameterization, they just ignore that. So this is very interesting. Like, data-driven science in this field can be incredibly impactful by replacing the microparameterizations. Everything else is first principles. So the Navier-Stokes equations, we really understand those. It's very fascinating that such a complex process of atmospheric physics can actually be compressed in a single equation, or a set of equations, very, very small number. But they're computationally very expensive. So now there is some trade-off between the machine learning thing, which is the microparameterization as manually crafted models, like these feature engineers, when they did this for in the machine learning field in computer vision, like there were lots of papers how to feature engineer a cat, how to recognize a cat based on pokey ears and pointy ears and stuff like this. That all went away with the advent of CNNs and machine learning. I expect a similar thing going to happen in climate sciences very, very soon. Like all these microparameterizations, manually crafted, they'll all go away with machine learning-based or observation-based data-driven methods. That's the first step.
Do you think there's hope in that world where it's all based on the parameterization? It's replaced by machine learning.
Yes.
Is there any hope of explainability in that, or essentially we verify that is somewhat accurate and then we just use it?
That's a great one. So I have a lot of discussions with these climate science. Actually, it was a huge discussion. I gave a similar talk at the AI for Good Summit. There was a UN summit on AI for Good in Geneva 2 months ago. Very similar talk, and the discussion was all about with the scientists, well, how do we understand? Because we use these climate models to understand effects. What they very often do is they run an idealized Earth, which is called the aqua planet. So it's just water. It's the same size of the Earth, but it's just water, to understand atmospheric effects. You cannot do this with machine learning models because they have the land encoded into the model somehow. You can't turn off components. They can easily, in a simulation here, as this one shows, you can easily turn off the land. Just say, I don't want land, go away land. Or they can turn off various aspects in order to drive their understanding, to play with the simulation, what a scientist does. The machine learning models can't. So this is a big part of the skepticism. In the machine, and your question was probably slightly different. I was just explaining it for the gaining insight with the scientific method. But your question was probably more about, can we understand what these machine learning models are doing? Or how do we verify those in isolation? We don't.
And yeah. It's more like, can we, for these heuristics that are currently hand-coded, can we use the machine learning model to help us understand?
I see.
It's like intuitions, right?
That would be possible.
The local climate.
That would be possible, I think. It's not super attractive in some sense because these manually featured engineered things are, if you listen to the leaders in the field, are going away. So this is replaced by data-driven methods, which is very much what's happening in computer science in the large scale. So they're just trailing behind. So this is why we as computer scientists, we should really help the climate field to move faster because it may be necessary to understand what's going on. So that's kind of what I took up as my job a little bit to help. Yeah.
So you mentioned like the weather predictions are fairly accurate within a week, but it's much more challenging after that. Do you think that's a problem more just on the model itself hallucinates more, or more maybe the data, just the cloud data is not enough, you need some other earthquake, other data to be incorporated in?
That is a great question. Let me repeat the question. So a colleague mentioned that, I mentioned earlier that the weather prediction is actually quite accurate within a certain time horizon. And you asked why it's not accurate further in the future. The reason for this is mainly that you train a model with a certain horizon. Like I say, I want to predict the weather 6 hours into the future, or 12 hours, 18 hours. And so if I would train a model going further into the future, that's problem number one, right? Okay. Let's stick to this. You train model for a fixed horizon. You can deal with that with autoregressive application of the model. So that is possible. GraphCastNet does that. So that works well. The more fundamental problem is that it's a chaotic process. I mentioned this, right? So in any chaotic process, the further you go into the future, the higher you go away from your starting point exponentially fast, right? So now the possible state space into the future grows exponentially large, and now the model needs to identify one state in that state space reliably from the starting position. So with any chaotic system, it's getting exponentially hard to predict it into the future, and even the simulations are not very good at this, right? This is why the simulations do very, very small time steps for various other reasons like CFL and whatnot, but let me not go into detail. And I think it's fundamentally challenging to go further into the future because of this chaotic nature of the problem. Weather is really chaotic, and it's really like these random storms. Like a couple of days ago, we had a tree come down in our house, and when was it? On Saturday, there was this like wind coming out of nowhere here, like literally nowhere, like took down 2 trees and was gone. It was pretty massive, and it was completely random. I don't know why. Oh, there's a...
We have a question online. Yeah, please unmute and ask your question.
Yeah, hello, yes. So my question was related a bit with this topic of autoregressive models and the notion of feeding the output from the simulation into the model and extrapolating into the future. And we know that when models are when there's uncertainty, there is no way to predict long way into the future.
Yeah.
So my question too is that I come from the computer vision field, and I've been through this transition where we went from classical model-based techniques to data-driven things, and the field was really driven by the way benchmarks were created and how evaluation was done.
Yes.
And computer vision data sets are even today full of problems, which have to do with invisible biases in the data. So what I'm trying to understand is in climate science and atmospheric modeling, you talked about this notion that we have like 40 years of data of the Earth, and the data used to be very sparse, and it's getting better.
Yep.
So like, this is like not a, I don't know how, like, this is like almost like a question to ask about what is your opinion about like the way evaluation is done today. Is it sufficient? Do you think there is more research needed for making the evaluation more scientific so that we can have more impact? Because when computer scientists and environmental scientists talk to the rest of the world, they are essentially trying to say, look, guys, there's a problem. We need to do something, right?
Yeah.
So this is a very fundamental thing, right? Like of how you evaluate. And can you share your views on that? Like,
Absolutely, I love that question. That is the killer question. So you're going to get a long and complex answer. But absolutely, the observation is that the computer vision field has been driven by benchmarks, ImageNet and many others, but most centrally ImageNet. So this field here, it has a data set. It's not a benchmark. It has a data set. That data set, as I mentioned, is pretty inaccurate if you go 30 years back. Essentially all, but I would say I would say practically all of the models that we have today for climate prediction, like Pangu weather, GraphCastNet, ForecastNet, all of these models have been trained on that data set, that ERA 5 data set. Typically what scientists there use is they use a region between 2010 and 2020 because that's when satellites came online. So there's a huge phase change in the data set itself when the satellites came online, because then the quality got so much better because we suddenly have much more assimilation data, and obviously. And this is what what's used as a training data, right? So now, what's the problem with this data set? This data set is great. It's actually one of the big European successes in machine learning, I would say, because usually all the innovation comes from outside of Europe in machine learning. But this thing, every weather and climate model is trained on European data here. But it is unfortunately not the resolution that we want. It's not the kilometer scale resolution that I talked about earlier. It's in fact somewhere between 25 and 15 kilometer resolution. And unfortunately, I didn't say this, but as you double the resolution, you cube the data storage because it's x by y by z. It's a three-dimensional problem. So it's relatively small. If you would have it at 1 kilometer resolution, I think it would be 1,000 times bigger again. So this data set is very coarse resolution. 15 kilometers is quite coarse, right? You would get one data point over Seattle, and then it would average like the whole city to 1 point. So not good. So that's one problem with the data set. The second problem, and that is even more problematic in my view, and people disagree on this, I have constant discussions, is how do you even understand how close you are to what's the loss function? What's the closeness metric between two climate fields? Everybody has a long discussion about this, and then at the end they all use MSE or RMSE. But if you look at RMSE can totally cheat. It can shift from one pixel, like pixel-wise RMSE, it's typically. It can shift from one pixel into another. Like if I have a very high loss somewhere, I can make up for it with a low loss somewhere else, right? And this is just like, I could report 100 degrees over Seattle. If everything else is really accurate, you won't see this in RMSE. So this is a huge problem, especially if you look at the accuracy of extremes. Like if you want to look at a good representation of hurricanes, there at any given moment on Earth, there's about one hurricane somewhere. But you can totally round this away and still get a good RMSE. And then you will have 0 hurricanes, and your RMSE metric looks great. So
exactly. So it has to do with this notion of rare events are more informative. And if you evaluate RMSE, then you are essentially always going to get a good good
good
answer
average.
because
Yeah.
the rare events are rare.
And this is what fooled us, yes. And so we had a lot of discussion. So there is a thing that's called the extreme forecasting index. So the extreme forecasting is just intuitively what they do is they look at the distribution of values and they look at the tail. Like this is actually what you want. You don't want RMSE over all the values. You want to make sure you represent the tails well. And this is a different loss function now. And then there's also something that's similar to CRPS. If you're a computer vision person, you probably know CRPS. That's a perception metric by humans somehow. You can define that also for these fields, for these climate fields. So the problem is, though, that most people still use RMSE, and it's still an ongoing debate, what is a good loss function, because it's not so clear. The EFI has some problems because it overemphasizes the tail. The CRPS is not really designed for it. So yeah, I mean, if you have a good idea, we should join forces and come up with a good loss function. It's very problematic, I think.
Okay.
Huge issue. And then on the side of benchmarks, there are multiple efforts. There is a WeatherBench. There's a leaderboard. It's called WeatherBench for weather prediction. There is a similar one that's a climate bench. The difference is just that WeatherBench is one trajectory for 7 days or so. A climate bench is 10 years, multiple trajectories, but otherwise the same thing. But everybody uses this ERA 5 data to train on the past, which is also a problem, by the way. The next problem with ERA 5 is it's the past. Right? So you're going to learn the CO2 concentration in the atmosphere from 2010. Right? And how do you think this will represent the CO2 concentration in the atmosphere in 2040, which is more?
Right.
So you have the wrong, it's harder than images because the problem is non-stationary. Like image detection is stationary. A cat looks like a cat 10 years later, it's still a cat. The atmospheric state 10 years later has a very different physical composition. So there's a whole lot of interesting scientific problems how we could now look at the trend, because we know the trend of CO2 going up. We know what's happening in this data set in the last couple of years, actually. We see that the impact of the trend. Could we extrapolate that trend somehow? But that's a little bit hokey pokey as well. But you see the problems, right? So it's not so easy.
Yes. Thank you for the deep discussion.
Thank you.
Appreciate it.
It's a great question.
And thanks for the great talk.
Yeah, thank you.
Any other questions online? I don't see anybody else with a hand up. Any other questions here? I think we've exhausted all the questions. Thank you once again, Torsten, so much for the great talk.
Thank you very much for having me.